Welcome to This Explainer. Today, we're jumping right into the journey of a spark. We're going to start with a baffling, invisible scientific mystery from the 19th century and follow it all the way to the massive, globe-spanning power grid that is literally charging the device you're using right now. We're breaking down the absolute magic of electromagnetic induction and the exact science of how we pull electricity straight out of thin air.
To really get this, we have to rewind to the 1820s. Scientists back then had just figured out something huge. Thanks to a guy named Oersted, they realized that an electric current could actually create a magnetic field. But naturally, that sparked an immediate follow-up question. If electricity makes magnetism, could a magnetic field create an electric current? It seems like a no-brainer, right? But for a solid 10 years, some of the absolute brightest minds on the planet were completely stumped. They tried literally everything to get a steady magnet to produce electricity, and they just kept failing. Then, 1831 rolls around, and we get this absolute bombshell discovery by two physicists working independently, Michael Faraday in England and Joseph Henry in the US. They finally found the answer. And the answer was yes, but with a massive universe-defining catch. It only works if the magnetic field is changing. You could sit a perfectly steady magnet inside a coil of wire for 1,000,000 years, and you know what you'd get? Absolutely nothing. Zero voltage. Change is the secret ingredient here. Which brings us to a foundational rule of our universe, Faraday's law of induction. Basically, it tells us that the induced voltage in a coil is directly proportional to the rate at which the magnetic field through that coil changes. So making electricity, it requires dynamic movement. It requires flux. You have to keep things moving because the voltage only exists while that field is actively changing. Okay, so how do we actually force that change to happen in the real world? Well, Faraday laid out 3 specific physical actions to induce a current. First, you can just physically move a magnet into or out of a wire coil. Second, you can flip that around, move the coil itself toward or away from a stationary magnet. Or third, you can change the current running through a completely separate nearby coil, which then alters the magnetic field passing through your first coil. It's so brilliant because it drives home the core concept. Every single one of these methods relies on continuous, non-stop change. The field has to be increasing, decreasing, or rotating. Once Faraday cracked that code, the obvious next question was, how do we get more juice? How do we scale this whole thing up? Turns out, it comes down to 3 simple variables. You can swap in a stronger magnetic field, because a stronger magnet just flat out induces more voltage. You can add more turns of wire to your coil. More turns means you're capturing way more of that changing field. Or you just increase the speed of the change itself. Move that magnet faster or change the field more violently, and boom, you get a much greater voltage. But the universe never just hands out free energy, right? There is always a cost of doing business in physics, and that cost is perfectly captured by Lenz's law. Lenz's law states that the direction of an induced current will always flow in a way that opposes the change in the magnetic field that originally produced it. And this all boils down to the absolute law of the conservation of energy. You simply cannot create energy out of nothing. Let's make that abstract idea a bit more tangible. Imagine you're physically holding a magnet, and you shove the north pole of it into a wire coil. The induced current inside that coil instantly starts flowing in a direction that makes the end closest to you act like a north pole too. Now, what happens when 2 north poles meet? They repel each other. So you actually have to physically push against that magnetic repulsion. You're doing mechanical work to force that magnet inside. That work, your physical sweat equity, is the exact source of the electrical energy that's now generated in the circuit. Think about it. If the current helped pull the magnet in, the magnet would just accelerate on its own. We'd have infinite free energy forever, and, well, that completely breaks the laws of physics. So let's take all this theory and build something real. Our first major application is the generator. A generator is, at its core, a device that turns mechanical energy into electrical energy. How? By taking a coil of wire and physically rotating it inside a magnetic field. Because that coil is constantly spinning, the magnetic field passing through it is constantly changing, increasing, decreasing, reversing, over and over. That constant rhythmic change induces a voltage that continuously alternates its direction, which is exactly why we call the output alternating current, or AC. And we're not just talking about lab experiments here. This is how our entire modern world gets its power. Think about those massive power plants. They all rely on giant generators driven by spinning turbines. And what spins those turbines? It might be high-pressure steam from burning coal or natural gas, or heat from nuclear fission. It could be the raw kinetic energy of water falling through a hydroelectric dam, or it could be giant wind turbine blades catching a breeze. Regardless of the source, the mechanical energy of that spinning turbine is directly converted into electrical energy via electromagnetic induction. Almost all the electricity you use every single day comes straight from Faraday's spinning coils. But right when we think we've got it all figured out, we run into the villain of our story: wire resistance and power loss. We have this massive logistical nightmare. How do we get massive amounts of power from a plant that's, say, 50 miles away to your living room without losing all of that energy along the journey? See, when current travels through a long wire, that wire naturally fights back with electrical resistance. And because of that resistance, a huge chunk of your precious energy just burns off as heat into the open atmosphere. Enter the hero of the power grid, the transformer. It is an incredibly elegant device that uses induction to change the voltage of an alternating current. It's basically just two coils of wire, a primary and a secondary, wrapped around the same shared iron core. When alternating current flows into the primary coil, it creates a continuously changing magnetic field inside that iron core. That changing field then passes right through the secondary coil, and just like that, it induces a new voltage. But remember, this is absolutely crucial. It only works with AC power. If we use direct current, or DC, it would just create a steady, boring magnetic field. And as we learned earlier, a steady field induces zero voltage. Here's how we manipulate this to our advantage. The relationship between those two coils all comes down to proportional reasoning, governed by the transformer equation. If we want a step-up transformer, we just give the secondary coil more turns of wire than the primary. The voltage shoots up, but because power is strictly conserved, the current proportionally drops down. On the flip side, a step-down transformer uses fewer turns on the secondary coil. The voltage drops down to a safer level, so the current shoots up. You literally can't cheat the system. If voltage goes up, current has to go down.
Let's look at something you probably use every day, your phone charger. Tucked inside that little brick is a step-down transformer. It pulls 120 volts of AC right from your wall outlet into a primary coil that has 600 turns. But the secondary coil inside, it only has 25 turns. That drops the voltage by a factor of 24, giving you a nice, perfectly safe 5 volts for your phone. But check out what happens to the current. If it pulls half an amp from the wall, the current gets boosted by that exact same factor of 24, delivering a solid 12 amps to your phone battery. Let's check the math. 120 volts times half an amp is 60 watts. 5 volts times 12 amps is 60 watts. The total energy is perfectly, beautifully conserved. So why does stepping voltage up and down matter so much when we look at the big picture of the power grid? Well, let's look at the brutal math behind transmission lines. The formula we have to worry about is power lost equals current squared times resistance. Look really closely at that. It relies on the square of the current. That makes high current the absolute ultimate enemy of a power grid. If you just double the current in your lines, you don't double the heat loss, you quadruple it.
Let's run a quick, honestly jaw-dropping comparison just to prove this. Imagine a power plant trying to send 500,000 watts of power over lines that have 10 ohms of resistance. If we send it at 10,000 volts, we'd need 50 amps of current. 50 squared is 2,500 times 10. That means we lose 25,000 watts as pure, useless heat. That's a 5% loss right off the top. But what if we use a step-up transformer at the power plant and crank that voltage all the way up to 500,000 volts? Suddenly, our current plummets down to just 1 amp. 1 squared is 1, times 10 is 10. We lose only 10 watts. 2,500. Just let that number sink in for a second. By increasing the transmission voltage by a factor of 50, the amount of power we lost didn't just shrink by 50. Thanks to that squared rule, it shrank by a factor of 50 squared. We literally saved 2,500 times more power from just evaporating as heat. And that right there is exactly why you see those massive, towering high-voltage transmission lines stretching along the highway. They're the absolute key to making sure the power actually gets to you. And that, incredibly, brings our entire journey full circle. We've gone from a totally unexplainable mystery in the 1800s to the hyper-efficient, massive grid that literally runs our modern lives. It's this beautifully violent dance of spinning turbines, opposing magnetic fields, and precisely balanced math, all happening continuously, completely out of sight. So I'll leave you with this thought. The next time you casually plug your phone into the wall, will you pause for just a second? Will you feel the ghosts of Michael Faraday and Joseph Henry and think about those countless invisible spinning magnets doing all that heavy lifting right in the palm of your hand? Thanks for diving into this with me. Keep wondering, keep learning, and I'll catch you on the next explainer.